Okay, so when we last left off in chapter 5, we were discussing meso compounds in part. These are compounds that, although they have chiral centers, are not actually chiral molecules because these meso compounds possess an axis of symmetry. In an axis of symmetry, the substituents and the components of your molecule are identical on both sides of the axis of symmetry, on both sides of the axis of symmetry. Essentially, the axis of symmetry can divide the molecule into two identical portions. So for example, in this case, depending on the stereochemistry, we either have a meso compound that contains a clear axis of symmetry, or a chiral compound where there is no axis of symmetry present. So in order for there to be an axis of symmetry, the substituents and their stereochemistry must be identical on both sides of the axis of symmetry. Does that make sense to everyone? Does this look familiar to everyone? And just for completeness sake, would this third structure be chiral or meso? It would be meso. Yep, exactly right, because it has a clear axis of symmetry. Perfect. Sorry about that, accidentally ended up. Go. Okay, so this compound would be meso. Okay, so let's talk about chiral centers. So a chiral center is a point in the molecule where 4 different groups or atoms are attached to a carbon. So for example, in this case, this carbon is a chiral center because there's a hydrogen, bromine, a butyl, and a pentyl group. All of the groups are different. Now, if the two substituents on a carbon are the same, there's an axis of symmetry and that carbon is achiral. So for example, only this center in this molecule is a chiral center. The second carbon here is not a chiral center. And the reason for that is that we have 2 identical substituents attached to the same carbon. And as a result, there is an axis of symmetry for this carbon. Does that make sense? So in order for you to have a chiral center, there needs to be 4 different substituents attached to your carbon. Does that make sense to everyone so far? Okay, so then let's keep going now and let's look at the following molecule and let's try to identify our chiral centers. So first things first, we're going to add our hydrogens. So we have 2 chiral centers in this case, here and here, as each of these centers are attached to a total of 4 different substituents. Does everyone understand the process for identifying chiral centers? Always do a check at the end just to make sure that the molecule itself is not meso before you declare the molecule chiral. So first you look for chiral centers, 4 different substituents attached to a carbon, and then you check whether or not the molecule is meso by looking for axis of symmetry. Does this make sense to everyone? Okay, let's keep going then. So thinking about chirality centers in chiral molecules, groups are considered different if there is any structural variation. If the groups cannot be superimposed, if detached, they are different. So for cyclic molecules, we can compare by following in each direction across a ring and counting our carbons clockwise and counterclockwise. If the cyclic molecule has the same groups with the same number counting, then what we can conclude is that the center is not chiral. So for example, methylcyclohexane is achiral. The reason being, one, it has a clear axis of symmetry if you want to use that argument, but also if you label and you count your carbons clockwise and counterclockwise, you notice that at each carbon, so for example, at this carbon here, we have the same substituents. And because we have the same substituents at each carbon, this center, all of the two substituents attached to this center are identical. And as a result, this chiral center is achiral. Another argument that you could use is that if you were to draw out each of your substituents as alkyl groups, it's pretty easy to see that we have two identical substituents. And as a result, the methylcyclohexane does not have a chiral center. If we look at methylcyclohexanone, however, it does not possess an axis of symmetry. Resonance is an entirely different idea with respect to chirality. Resonance is just serving to define the average bond length and the actual bond length, strength, and approximate distribution of electron density in your molecule, while chirality is concerned with symmetry and whether a center, whether a carbon containing multiple substitution patterns, whether a carbon containing 4 unique substituents possesses an axis of symmetry, and whether or not you can draw non-superimposable mirror images for your molecule. And chirality is very much concerned, and chirality and stereochemistry is very much concerned with molecular shape, as different stereoisomers have different molecular shapes, different 3D shapes. So for methylcyclohexanone, as we see, if we count our carbons clockwise and counterclockwise, we notice that in the red counting method, at carbon number 2, we have a methyl group. Okay, well, in the blue counting method at carbon number 2, we just have a hydrogen. Because we have different substituents at the same carbon counting number, that implies that our two substituents attached to this carbon are different. And as a result, this center would be a chiral center. This is pretty straightforward to see if you draw out there we go. And we can clearly see that this molecule possesses a chiral center because the two substituents are clearly different. So always be on the lookout for axes of symmetry when assigning whether or not a molecule is chiral and whether or not a stereocenter is a chiral center. Does this make sense to everyone so far? Okay, let's keep going now. So just to showcase this counting method once again, so we count clockwise in one counting method. We count counterclockwise in the second counting method. And we look for the same carbon number. Are our substituents identical? And in this case, I see 2 hydrogens attached to this carbon in both cases. So it looks like both substituents attached to this central carbon are identical. And as a result, this center is not a chiral center. Comparing this to the 2-methylcyclohexanone, if we count clockwise and counterclockwise, we immediately notice that if we compare, on carbon 6, we have our ketone in one structure, while in carbon 2, we have our ketone in the second counting method. Because our substituents are different attached to this central carbon would be a chiral center, and the molecule itself, because it lacks an axis of symmetry, would be a chiral molecule. Does that make sense? Okay. So let's work on the following example, and let's label our chiral centers in the following molecule. And we won't worry necessarily about the potential for meso compounds right now. So looking for our chiral centers, we need to have 4 different substituents. So we'd have a total of 1, 2, 3 chiral centers in this first molecule, while in the second molecule, we'd have 1, 2 chiral centers with the note that there may be meso compounds. For example, if we have a stereochemistry that looks something like this, well, this compound is chiral. However, the symmetrical variants, which look something like this, are meso because there's a clear axis of symmetry. Do these first examples make sense? Any questions on this example where we're asked to identify chiral centers in our molecule and identify stereocenters in our molecule? So let's give it a shot now. And I'd like you to take a look at the following 2 molecules, and I'd like you to identify the chiral centers in each molecule. And I would encourage you to use the annotate tool to label your carbons that you would view as chiral carbons. Let's spend about 3 minutes on this example. Don't be shy to share your work in the chat or verbally, and I'd be happy to answer any questions posed in the chat or proposed verbally. So let's focus on identifying the chiral centers in the following molecule. And I would prefer if a few students would contribute their responses using the annotate tool and explicitly labeling on these structures which carbon they consider chiral. Perfect. So we have one proposed assignment for the whoops. Sorry about that. So we have our first proposed assignment for the chiral centers. I'll redraw this molecule so that other students have the opportunity to share their proposed responses. Let's keep working on this example and don't be shy to contribute your own perspective to this discussion. Let's try to get a few more responses from students using the annotate tool or by posing their responses in the chat. And let's try to get a pool of student responses for both of these questions. And we'll discuss in about another minute to a minute and a half. And really don't be shy to contribute your responses using the annotate tool or in the chat. And remember, the annotate tool is accessible using the meeting options feature and the view options feature in Zoom. Would anyone like to share some proposals? Ah, perfect. So we have a proposal for the chiral centers in the second compound. Let's spend about another 30 seconds on this example. And if anyone else would like to contribute their proposal for their chiral center assignments, don't be shy to break out the annotate feature and draw and label your proposed chiral centers. Okay, so let's discuss this example. So first things first, we're going to draw out each of our substituents. As we can clearly see in this case, each of our 2 carbons have 4 different substituents. So in turn, we have 4 chiral centers. In this second case, we only have 1 chiral center because if we look at this carbon, we see that we have 2 identical substituents. So as a result, this molecule only has 1 chiral center. Does that make sense to everyone? Make sure you're on the lookout for identical substituents and axes of symmetry. Any other questions on this example before we move on? Okay, so let's keep going with this and let's talk about drawing enantiomers. So remember, we call enantiomers a pair of molecules that are non-superimposable mirror images. Think your left and your right hand. They're mirror images that cannot be superimposed. Enantiomers have the opposite configuration at every chiral center stereocenter. So there's a trick for drawing enantiomers quickly and efficiently. First, you draw your molecule, then you can draw a mirror plane behind your molecule, under your molecule, or to the right of your molecule. Now, all you have to do then is you draw the mirror image of the molecule across the mirror plane. So for example, if you're looking at the mirror plane behind your molecule, what you're going to do is you're going to invert the wedge dash notation for every stereocenter, and you're going to draw the molecule in the exact same way. So to showcase this, if we're looking at a mirror plane, and we're taking the following structure and trying to draw its enantiomer, We draw the skeleton exactly as we've originally drawn it. So we draw the same skeleton, but we would reverse the stereochemistry and the dash wedge notation for that stereo center. And that in turn gives us a set of non-superimposable mirror images. Does this idea make sense to everyone? Does this idea of drawing enantiomers by inverting the molecule across a mirror plane make sense to everyone? So to give everyone a sense of how this would function in practice, if you happen to have like a handheld mirror handy or something of that sort, that's really useful for these kinds of problems and examples. It makes it a little bit easier to see how things are reflected and how the mirror image is generated across a mirror plane. So let me make a model of this structure just to further demonstrate and help you visualize what's going on in this case. Okay, so here is our original molecule. Don't worry much about the cyclohexane ring. I want you to focus more on this side chain here, as that has our chiral center. Okay, does everyone notice that initially this methyl is pointing towards us? Does everyone see that this methyl is pointing towards us in our original structure? Okay, so if we invert our molecule across the mirror plane, what we are functionally doing is we are pretending that behind our molecule, sort of like where I put my hand, there's a mirror plane, and we draw the mirror image of our molecule. And in practice, what that means, the mirror image of your molecule will have the same skeleton, but an opposite configuration. It will have an opposite configuration at every chiral center. So does everyone notice in the mirror image of your molecule that the stereochemistry at your chiral carbon has been reversed? Does everyone see how the stereochemistry, the arrangement of substituents at this carbon, is now different? Perfect. So there's another way of thinking about mirror images. There's another way of looking at mirror images. So let's look, for example, at the following two structures. So here's our original structure, and we're asked to draw the enantiomer. So to do that, we draw our skeleton exactly the same, and we invert the configuration at each of our chiral centers. Does that make sense to everyone, this process of inverting the configuration while keeping the skeleton the same to draw the enantiomer of a compound? Does everyone see how these two compounds, even though they are mirror images, They cannot be superimposed. The stereochemistry at each center is different. Okay, so let's look at another way of drawing enantiomers. In this case, we're looking at a mirror plane below our molecule. So what you're going to do is you're going to invert your molecule vertically while retaining the same dash wedge notation. So for our example, for the following amino acid, what we are doing is we are inverting our entire molecule about the vertical axis. So we're essentially flipping our molecule from the vertical axis, and we're drawing our stereocenters exactly the same. Now, if we take a look at this inverted structure, so let's showcase what this inverted structure will look like. Okay, so here is our inverted structure. Does everyone notice how this bottom structure, we flipped the entire skeleton on the vertical axis, and we've kept the stereocenter exactly as is. This methyl is pointing out towards us, right? Does everyone see that? Now, we can rotate this molecule. We can rotate this molecule in a way that more accurately depicts the stereochemistry at this carbon. So if we rotate this molecule, we see that this structure is equivalent to the following drawing. And I just want you to tell me, is this methyl group after we've rotated our molecule? We haven't changed anything in terms of which enantiomer we're looking at. We're just rotating this enantiomer picture to get a better sense of what's going on. Where is this methyl group? Is it pointing towards us or away from us? Where is this methyl group? It's pointing away from us. So we'd write this methyl group as having a dashed stereochemistry. And here we can clearly see that the stereochemistry at this chiral center is different in these two molecules. In fact, these two molecules have the exact opposite stereochemistry at each of their stereocenters. Does that make sense to everyone? Does everyone see why we have enantiomers in this case? Okay, so you can also think of this, the same rotation that I did with a model kit can also be drawn by hand by rotating your carbon-carbon bonds. And here we can very clearly see that both of our stereocenters have the opposite stereochemistry. So let's take a moment now, and I'd like everyone to try drawing the enantiomer of the following molecule. And I'd like you to try to use the bottom mirror plane method, and you can also try with the vertical mirror plane method. Let's take about 2 to 3 minutes, and let's have some students draw out the enantiomer for this molecule, and let's try drawing the enantiomer using both methods. And remember, don't be shy to share your responses using the annotate tool. And there are multiple spaces for students to draw, so don't be shy to contribute your own response as you go about this problem. So we have our first proposed structure. So we have our first proposed structure for the enantiomer of our initial compound. Perfect, perfect. So let's keep working through this example and let's try to see, would anyone like to contribute an enantiomer drawn using the bottom mirror plane method? Or using the vertical mirror plane method. Either is fine. Would anyone else like to contribute their enantiomer for this compound? Just give everyone a little bit more time to work through this example. And really don't be shy to use the annotate feature to contribute your proposed responses for the enantiomer of this compound. You can also send a picture or image file, and I'd be happy to look that over as well. And we'll discuss this example momentarily in about another 30 seconds to a minute. Okay, so the responses that I've seen so far are encouraging. It's good to see that students are working through these problems and are proposing their solution. I find that's where you often get the most benefit in this process. So allow me a moment to clear these proposed drawings, and then let's discuss the instructor solution. So if we're using the vertical mirror plane method, we're going to invert our molecule about the vertical axis, and we're going to keep each of our stereocenters drawn exactly the same with the same dash wedge notation. This has actually flipped the stereochemistry of each of our stereocenters implicitly. So let's take a look at why that is. So There we go. Okay, so let's take a look at a model for this structure. Let's take a look at a model for this structure. Okay, so here we go. So we have our ketone, it's been flipped, we flipped this entire molecule on the vertical axis. We're looking at this, the structure for this enantiomer here. And one thing that I want us to help visualize, one thing I want us to want to help us visualize is how this molecule is in fact an enantiomer. So with a little bit of rotation, what we're going to do is we're going to rotate this molecule, and now we're just going to draw what we see after rotation. This is just to show that this molecule, this other way of drawing this molecule, more clearly shows that we do in fact have an enantiomer. So as we see, if we redraw this molecule that we obtained by flipping this starting compound along the vertical axis, we've drawn the enantiomer, and in this case, it's very clear to see that we have a different stereochemistry at each of our carbons, and so this structure is in fact an enantiomer. Does that make sense to everyone? Does that idea make sense? Does everyone see that this is in fact an enantiomer? Okay, perfect. So just to showcase the other method, so if we draw the same skeleton and just invert every stereocenter using our previous method, this is another way of drawing our enantiomer. Both of these structures, these two structures that we've drawn, are different ways of drawing the same enantiomer. These two structures, the structure before and after inversion, are different. These are different enantiomers. And the key deciding factor between whether a set of compounds are identical and just drawn differently, or if they're different compounds, is the fact that different enantiomers will have a different configuration at each of our stereocenters. Does that make sense? Does that make sense to everyone? Any questions so far? Okay, let's keep going then. You can also invert your molecule using a mirror plane next to your molecule. So in that case, you invert your molecule horizontally while retaining the same dash wedge notation. So does everyone see sort of, if you put your hand up to a mirror, that this molecule has been flipped? So let's look at this with the video. Okay, so let me get that set up. Here we go. Okay, so we have our original structure here. Let me get the methyl group with the right stereochemistry. Okay, so if you want to invert your molecule across the mirror plane, you pretend like there's a mirror plane on the side of your molecule, and all you do is you invert the skeleton of your molecule horizontally and draw each stereocenter exactly the same. So let me show you an example of this. So here is our original molecule, and here is the mirror image. Does everyone see? Here's the original molecule, Here's the mirror image. Does everyone see that? This process of inverting across the horizontal plane. Here's our starting molecule. And here's the enantiomer, the mirror image. So let's prove to ourselves that these two compounds are in fact enantiomers. Let's prove that we actually have drawn enantiomers. So if we take a look at our, so if we take a look at our enantiomer, which looks something like this, we can show by rotation that our drawn structure is in fact an enantiomer. So first and foremost, what we're going to do is we're going to rotate our molecule. We're going to rotate our molecule such that the skeleton is now drawn in the same way. And as we notice, compared to our original structure, where we had a wedge, where the methyl was pointing towards us, in our enantiomer, where is the methyl group pointing? In our enantiomer, where is our methyl group pointing? Is it pointing towards us or away from us? Is it a dash or a wedge? It's away from us, exactly. So as we can see, these two depictions of our molecule are different chemical species. They're enantiomers. Does that make sense to everyone? So it's always important to prove to yourself when you try to draw an enantiomer that in fact the stereochemistry at each center is different. And we'll talk about a more efficient way of assigning stereochemistry later on in this chapter. So to apply what we've learned, I'd like everyone to try and draw the enantiomer of the following molecule. I'd like you to try and draw the enantiomer of the following molecule. And I would recommend in this case using the horizontal mirror plane method. And remember, there's plenty of space. There's even some space right here as well. So if you want to try drawing your proposed structure for the enantiomer, don't be shy as well. There's plenty of space on the board for the entire class to write and share their solutions. Yep, that structure looks great. It's inverted about the horizontal plane, but you've kept each stereocenter drawn in the same manner. Exactly right. So let's draw out this horizontal inverted enantiomer. So we draw our skeleton, and we keep the skeleton exactly the same. However, we've inverted the skeleton along the horizontal axis. And each of our stereocenters is drawn with the same dash wedge notation. Does this example make sense to everyone? Does this example make sense for drawing the enantiomers? Okay, so let's keep going now and let's talk a little bit about optical activity. Let's talk a little bit about optical activity. So Light restricted to pass through a plane is known as plane polarized light. And a polarimeter measures the rotation of plane polarized light that has passed through a solution. The light source passes through a polarizer and is then detected at a second polarizer. The angle between the entrance and exit planes is known as the optical rotation. Now, when plane polarized light passes through solutions of achiral compounds, it retains its original plane of polarization. Critically, solutions of chiral compounds rotate plane polarized light, and the molecules are said to be optically active. So, for example, if we pass a sample of plane polarized light through a sample of organic molecules, the plane polarized light ends up being rotated. And this change, this degree of rotation, depends both on your sample concentration and your sample's identity and stereochemistry. So, plane polarized light is rotated when it passes through solutions of optically active compounds. And this is measured using a polarimeter, where rotation in degrees is known as alpha. If there's clockwise rotation, it's dextrorotatory, and it's depicted with a positive sign. Anti-clockwise rotation is levorotatory, depicted with a negative sign. Now, specific rotation is a standard measure of the optical rotation of an optically active compound. Now, what's really cool is that specific rotation of enantiomers is equal in magnitude but opposite in sign. Now, it's really important, and I want to emphasize this now, that specific rotation, it depends on what enantiomer you're looking at, but it's not directly correlated with a specific stereochemistry. So for example, minus and plus are not correlated specifically with R or S. It depends on the compound you're looking at. So if we look at tartaric acid, for example, and we look at two enantiomers of tartaric acid, the minus tartaric acid and plus tartaric acid, as we can see, the specific rotations have the same magnitude but opposite sign, which is commonly seen when we have two enantiomers. Does that make sense to everyone? So we'll talk more about R and S. This is the standardized method for assigning the stereochemistry at each stereo center. And we'll talk more about that momentarily. Okay, so again, one thing I want to emphasize, the sign and magnitude of the optical rotation depends on the compound that you're looking at. What we do know is that enantiomers of a compound will have the same magnitude but opposite sign for their optical rotation. So again, there's no simple relationship between the RS assigned stereochemistry and the direction of optical rotation. Now, specific rotation itself is compound and temperature dependent and must be determined experimentally. It's typically used as a measure of a sample's optical purity and a measure of the relative amount of each enantiomer in a mixed sample. So, one thing that I'd like you to note is that we have two compounds, chloroform and acetic acid, that have an optical rotation of 0. Would someone like to explain why do these compounds have an optical rotation of 0? What's so special about chloroform and acetic acid that would give them an optical rotation of 0? What is that a sign? What does that tell us? If we have an optical rotation of 0, are these molecules chiral? Yep, so both of these molecules with an optical rotation of 0 are not chiral. You'd see the same phenomena if you had a meso compound as well, where you'd see an optical rotation of 0. Does that make sense to everyone? Does this idea make sense? Okay, so let's keep going with this. So in many cases, one enantiomer of a compound has a greater biological activity or the desired biological activity. I mean, biological systems and receptors, by their very nature, as they're built from chiral components and they have a defined molecular shape, these biological systems and the receptors in biological systems are chiral, and they can differentiate compounds based on their configuration and shape. Amino acids that comprise peptides and proteins are chiral, and most of them have an S configuration except for cysteine, which we'll talk about why momentarily. Now, different molecules will have different binding affinities and bind to different receptors based on their configuration and shape. So, with that in mind, if us as chemists, if we're designing and synthesizing molecules with the goal of affecting a unique biological response, we want to be able to determine the purity of our sample and the amount of each enantiomer present in our sample. You can think of this receptor analogy sort of like shaking hands. You can tell intuitively whether you're shaking hands with someone using the right or left hand, because that interaction depends on the shape of each hand and the orientation of each hand. Okay, so that's the pitch for why this idea is important. We see this all the time in actually many known pharmaceutical agents. For example, only the S enantiomer of ibuprofen is biologically active. In the case of penicillamine, being able to distinguish between the enantiomers is even more important and determine the percentage of each enantiomer in a sample, because the S enantiomer can be used to treat chronic arthritis, but the R enantiomer is highly toxic. Thus, the enantiomers must either be separated or the S enantiomer must be prepared as a pure single product. Now, it's really important then that we have methods to determine the purity and amount of each enantiomer in a mixture. So that's the rationale behind this next method. Why is this method developed? Well, we need to know the enantiomeric purity, not only to assess the efficiency of reactions and separations, but also to determine the composition of mixtures and the amount of each enantiomer, because the enantiomers can have wildly different properties in terms of how they interact with biological systems. Okay, so that's my justification out of the way for this next section. In terms of measures of enantiomeric purity, enantiomeric excess, or EE, is defined as the percent of a desired enantiomer minus the percent of the opposite enantiomer. So for example, if your mixture has 70% of the desired enantiomer and 30% of the undesired enantiomer, EE would be 70% minus 30%, which gives us 40%. EE is probably the most common measure and the most common way of assessing and reporting the amount of each enantiomer generated in a reaction, because EE looks at the amount of one enantiomer that is generated in excess compared to the other enantiomer. Does this make sense to everyone so far? Okay, so another way of looking at this is we can look at percent EE, which is less common, and it's a measure of the percentage of the desired enantiomer. It's defined as the observed rotation for your sample over the optical rotation of the pure enantiomer. Now, the main reason I don't personally like percent EE is that the opposite enantiomer affects the observed mixture optical rotation. So these are the two ways we can measure the amount of each enantiomer and report the amount of each enantiomer in solution or in a mixture. Now, with that aside, we're now going to talk a little bit about how do we formally assign the stereochemistry and configuration at chiral centers. This is sort of the centerpiece of this chapter. And in this case, we're focusing on defining our configurations using the Kahn-Ingold pre-log system and the sequence rules put forth by IUPAC. Okay, so in this method, let me make a model to help us visualize what's going on. So in this method, what you're going to do is you're going to look at the 4 atoms directly attached to our chiral center and rank them in order of atomic number. The highest atomic number is assigned the highest priority. So for example, in this first case, bromine has the largest atomic number, so it would be priority 1. Chlorine has the next highest atomic number, so it would be priority 2. Carbon has the next lowest atomic number, so it would be priority 3. And hydrogen has the absolute lowest atomic number, so it would be priority 4. Okay. Looking at the molecule on the right, which would be the highest priority atom? Which would be the highest priority group? Sulfur, yep. What would be the next highest priority? Fluorine, yep. And what about after fluorine? Oxygen, yep. Perfect. So, just as a side note, if 2 atoms have the same atomic number, what you're going to do is you're going to make a list of each atom connected to each atom that is connected to the chiral center, and you're going to rank the atoms connected to the atom in order of increasing priority. If a list has a higher priority group, not the total priority, just highest group priority, period, assign that atom the higher priority. Now, in some cases, if the lists are identical, you're going to have to keep moving one atom away from the chiral center and ranking the atoms attached in order of increasing priority. One little catch that you need to be aware of is that multiple bonded atoms are equivalent to the same number of single bonded atoms. So, for example, you can think of a double bond as if the center So you can think of your double bond as if your center was bonded to an additional carbon. A triple bond, you can think of it as if this carbon was bonded to 2 additional carbons. So multiple bonded atoms are counted as the same number of single bonded atoms. So a double bond to oxygen counts as 2 bonded oxygen atoms. Okay, so we have our method for assigning priority. Let's talk about some examples for assigning priority. So let's suppose we have 2 atoms with the same atomic number. Then, so in this case, we have hydrogen, oxygen, and we have 2 carbons, right? So these 2 carbons have the same atomic number. So what we do is we look 1 over in our chain and we look at all the substituents attached to the next carbon in the chain. So in this case, we have a carbon and a carbon. And so what we're going to do now is we're going to look at all of the substituents attached to this next carbon in the chain. So in this case, attached to this next carbon in the chain, I have 1, 2, 3 carbons and a hydrogen. Comparatively attached to this carbon in the chain, I have 1, 2 carbons and 2 hydrogens. So going down my list, the carbons are identical, but I have a carbon compared to a hydrogen. So which group is higher priority? The carbon on the left or the carbon on the right? The carbon on the left, exactly right. Well, exactly correct. So the oxygen will be priority 1. The carbon on the left will be priority 2. The carbon on the right will be priority 3. And the hydrogen would be priority 4. Does everyone understand this idea when we're successively moving down our carbon chain, looking at the substituents attached to our carbon, and then ranking them in order of priority, which is based on atomic number? Does this make sense so far? Okay, now just to really hammer home this point, if a list has a higher priority group, higher priority period, not total priority, then you assign that attached atom the higher priority. So for example, looking at this carbon, we have oxygen as our highest priority, and we have 2 carbons, okay? Now we're gonna look at everything attached to these 2 carbons. So let's make our list. So attached to these 2 carbons, I have an oxygen, a carbon, and 2 hydrogens. Okay, attached to the carbon on the right, I have 4 carbons, 1, 2, 3, 4. Now my question to you is, what is higher priority? Oxygen or carbon? What is higher priority? Oxygen or carbon? Oxygen. So then, which substituent gets the highest priority? The substituent on the left or on the right? Yep, exactly correct. The substituent on the left. So we really want to make sure your priority assignments are correct because they're key to assigning the configuration using this IUPAC method. Do these 2 examples make sense in terms of assigning priority? Do these 2 examples make sense in terms of assigning priority? Okay. So just a reminder, multiple bonded atoms are equivalent to the same number of single bonded atoms. So let's try to assign priority at this stereo center, and let's look at each of our substituents. So in this case, at this substituent, we have multiple carbons. So now we have to look at all of the substituents attached to our carbon. So in this top case, we have attached 2 carbons and 2 hydrogens. In this bottom case, we have 2 carbons and 2 hydrogens. So we'll keep going. We see we have 2 carbons and 2 hydrogens. Well, at this further down the chain position, we only have a carbon and 3 hydrogens. In this case, we have a carbon and 3 hydrogens. And in this case, we have 2 oxygens, a carbon, and a hydrogen. Okay, so starting off at our first carbon set. Starting off at our first carbon set, we'd assign this group with the aldehyde as the highest priority as it has an oxygen. Next, in terms of our comparison, we see that it's a tie. We see that it's a tie between these top 2 substituents, but this bottom substituent will be the lowest priority because it only has a hydrogen, and hydrogen is lower priority. To break the tie between these 2 carbon substituents, we move down the chain 1 more carbon, and we look at all of the substituents attached to this next carbon in the chain. So we see we have a carbon compared to 2 carbons, and as a result, because carbon is higher priority than hydrogen, we'd assign this leftmost substituent as priority number 2, while the top substituent gets priority 3. Does that make sense? Does that logic make sense to everyone? Okay. So let's look at this next example where we're assigning priority when we have double bonds. And I'm going to rewrite this molecule. I'm going to rewrite this to more accurately show. Remember, a double bond is treated as a double bond is treated as multiple bonded atoms. So for example, if you have a double bond, it's treated as 2 bonded atoms. So I'm drawing this double bond out to reflect that this double bond is treated as if this carbon is bonded to 2 carbon atoms. Likewise, the triple bond is treated as if it's bonded to 3 carbon atoms. So now that I've redrawn my molecule to reflect the nature of my double and triple bonds, I'm now ready to do a comparison. Okay, so let's look. Oxygen is clearly priority 1. We're going to look at each of these carbons. So attached to this carbon, we have 4 carbons. Attached to this carbon, we have 4 carbons. So we still have a tie. We move down the chain. Attached to this carbon, we have 4 carbons. Attached to this carbon, we have 3 carbons and a hydrogen. And as a result, the group on the left is higher priority. Does that make sense? Does this logic make sense to everyone? You have to make sure your priority assignments are correct. Otherwise, this method doesn't actually function very well. Okay. So, what we're going to do in this method, we're going to assign priority to each group in order of increasing atomic number, and you're going to rotate your molecule so the lowest priority group is in the back pointing into the page. Now, to really showcase this, we're going to look at a pair of enantiomers because enantiomers have the opposite configuration at every chiral center. So, allow me one moment and I'm going to make a model for these 2 enantiomers, and we're going to look at and we're going to assign the stereochemistry at each position. Allow me one moment. I'm just putting together the two models to show them to you. And I would encourage you to make a model of these two enantiomers. Okay, so here are our two enantiomers. Here are the two enantiomers. Does everyone notice how these two molecules are mirror images? Okay, so let's start with this structure, okay? So in terms of arrangement, we see our hydrogen is our lowest priority, our bromines the highest, our chlorines are second highest, and our oxygens are third highest. So what we're going to do is we're going to rotate this molecule so our lowest priority group is in the back. Okay, so to do this, what I'm going to do is I'm going to bring my chlorine up. Okay, so I brought my chlorine up. And now what I'm going to do is I'm going to rotate my molecule so my hydrogen is in the back. Okay, so does everyone see I have my chlorine on top, my oxygen pointing to the right, my bromine pointing out towards us, and then the hydrogen's in the back. Does everyone see how this rotation occurred? Let me show this to you one more time. So starting off from our original snapshot with our hydrogen in front, I brought my chlorine up top, and then I brought my chlorine up top, and then I rotated my molecule so the hydrogen's in the back. Does everyone see that? Does that make sense? You can do this on paper. I've shown these steps that I just did with the model on paper, but I would recommend using a model kit. Let's do the exact same process for our second enantiomer. Okay, so in this case, we want to bring the hydrogen in the back. So we bring our chlorine up and we rotate our molecule so the hydrogen is in the back. Now, as we can see very clearly in this case, these two structures are non-superimposable mirror images. If we draw our two skeletons in the exact same way, our substituents are in different positions. Does that make sense to everyone? Does everyone see how we rotate our molecule to put the hydrogen in the back? As long as your hydrogen is in the back, this method, as long as your lowest priority group is in the back, you're good to go for the next steps. I always like looking at stereochemistry in the context of enantiomers, as it makes it very easy to check your work, because the enantiomers will obviously have different configurations. Okay, so let's look at our second example. And as always, the first thing I'm going to do is I'm going to make a model. Make a model of this structure. You're more than welcome to use a model kit on exams, so there's no reason not to make full use of all the resources available. So give me one moment just to put together a model of this structure, and then we'll be able to discuss. And I really would encourage you, during the time when I'm putting together a model, I would like you to consider also putting together a model using your own model kit. Okay, so we're looking at this first structure here. In this case, we have our hydrogen up top. We have our oxygen pointing out of the page. Our fluorine in the back. and our sulfur in the front. Okay, so now we're going to rotate this molecule so that our hydrogen's in the back. And one trick we're going to use is, first and foremost, if we know that our fluorine is in the back, what we can do is we can rotate our molecule like so, and now we have our hydrogen in the back. So now what we have to do is we just have to draw what we see. So in this case, we have our sulfur on top. We have our oxygen pointing out of the board. We have our fluorine pointing to the right and our hydrogen in the back. Does everyone see how we got that? So just starting off from scratch. Here is our initial structure. We notice the fluorine's in the back, so we rotated our substituents so that the hydrogen's in the back, and then we draw what we see. So we have our sulfur up top, our oxygen pointing to the left, and our fluorine pointing to the right. Does that make sense to everyone? Okay, we can do the exact same thing with our opposite enantiomer. We can do the exact same thing with our opposite enantiomer. So here's our opposite enantiomer. So we have our oxygen in front. So we have our oxygen in the front, our fluorine in the back, and our sulfur pointing. One moment. Here we go. So we have our opposite enantiomer. So we have our sulfur pointing to the left, we have our oxygen in front, and we have our fluorine in the back. What we're going to do is we're going to rotate our molecule so that the hydrogen is in the back, and then we're going to draw what we see. So in this case, the oxygen is up top, the sulfur is pointing out of the page, the fluorine's pointing to the right, and the hydrogen's in the back. As we can see very clearly, for both of our enantiomers, they have a different configuration and a different arrangement of our substituents. Does that make sense to everyone? Is this idea of rotating your molecule to put the lowest priority group in the back, does that make sense? Okay, so now that we've done all of that legwork, so this next page, so is there any specific convention for arranging the higher priority atoms in front? No, as long as the lowest priority group's in the back, this method will work perfectly fine. So I've also showcased other ways of rewriting different configurations and rotating different configurations using your model kit. Once we have set it up so the lowest priority group is in the back and the highest priority groups are in the front, we're going to place the remaining 3 groups in a plane, and we're going to draw a circle moving from the lowest priority group in the plane to the highest priority group. Okay. So well, this should be lowest priority number to highest priority number. Or the other way of thinking about it is you can draw a circle moving from the highest priority, which would be 1, to the lowest priority, which would be 3. Okay, so in this case, we have our priority groups with bromine being the highest and oxygen being our lowest. We're going to draw a circle and we're going to draw a line going from our highest to our lowest priority. And if your circle requires a clockwise motion to go from highest to lowest priority, so in this case, we have a clockwise motion to go from our priority 1 group to our priority 3 group, we designate this as an R configuration. So this stereocenter would be an R stereocenter. A counterclockwise rotation is designated as an S stereocenter. So in our enantiomer, as we go from priority 1 to priority 3, it requires us to move in a counterclockwise direction. And this counterclockwise counting from highest to lowest priority indicates that we have an S stereocenter. Does that make sense to everyone? You draw a circle going from the highest to lowest priority. If it's clockwise, we have R, counterclockwise, S. Does that make sense to everyone? Okay. So let's look at an example now, and this will be the last example that we work on for today. I'd like you to look at the following structure, and I'd like you to assign the configuration as R or S for this chiral center. If possible, I'd like students to use the annotate feature to label your group priorities, but I'd also like students to share their proposed configuration assignment in the chat. And we'll discuss this example in about 2 to 3 minutes. Perfect, perfect. So we have our first proposed assignment that this stereocenter is S. So let's clear and let's draw this. So in this case, bromine is priority 1, the ethyl group is priority 2, the methyl group is priority 3. We draw an arrow from the highest to lowest priority. We're going counterclockwise. So this stereocenter would be S. That's exactly right. Does that make sense to everyone? Does this idea make sense to everyone? Perfect, perfect. So this is a good stopping point for this first lecture segment.